In this video, I will discuss Quantum Well Infrared Photodetector, in short, QWIP. Before focusing on it, let's review the background theories. Max Planck's blackbody radiation and quantum well, which are the basics of infrared detection. For blackbody radiation, it is a matter of common experience that the surface of a hot body emits energy in the form of electromagnetic radiation. In fact, the emission occurs at any temperature greater than absolute zero, with the emitted energy being continuously distributed over all wavelengths. At low temperatures, below about 500 degrees C, most of the emitted energy is at long wavelengths, corresponding to infrared radiation. Much of the energy will be radiated at low wavelengths as the temperature increases. For example, the temperature of the flame is about 800 degrees C. A large enough fraction of the emitted energy has wavelengths within the visible spectrum so that the body glows. At 1500 degrees C, the spectral distribution has shifted sufficiently to the lower wavelengths for the body to appear white-hot as liquid ions. In 1900s, Planck presented a new form of the blackbody radiation spectral distribution based on his revolutionary hypothesis. He proposed the Planck spectral distribution law as well as one of the deductions of his theory. Before processing, let's first review the absorption coefficient, which should be taken into account as well. When radiation falls on the surface of a body, some are reflected and some are absorbed. For example, dark bodies absorb most of the radiation falling to them, while light-colored bodies reflect most of it. The absorption coefficient of a material surface at a given wavelength describes the condition of absorption. Thus, the Planck spectral distribution law becomes the formula of radiance, which is the thermal radiation power per unit area and steradian. Then, what is a quantum well? Start with the simplest model of a quantum well system, the infinite well model. The barriers of the potential well are assumed to be infinite, which is rather unrealistic. Still, as a first step, the infinite well model provides some insight. Considering an infinite quantum well oriented in the x direction, such that the carriers in the well are confined in it. Solving the Schrödinger equation with boundary conditions, it turns out that the energies of the carriers are discrete as proportional to the square of quantum numbers. One step forward, the finite well model provides a more realistic model of quantum wells. The walls of the well are in heterostructure and described by a finite potential, which is the difference in the conduction band energies of different semiconductors. Since the walls are not infinite, electrons can escape from the well. Solving the Schrödinger equation with relevant conditions, it can also turn out that the energy are discrete, but the wave function do not vanish in the wall this time. Gallium arsenide is used to construct quantum well infrared photodetectors. It is also widely used in semiconductor devices. It also plays a significant role in the high-frequency transmission field in wireless communication. The device of the Quantum Well Infrared Photodetector is designed as a layered structure, with spaced apart layers doped with aluminum atoms forming periodical quantum wells. Here, we discuss only inter-subband transition in the conduction band. A typical quantum well infrared photodetector consists 20 to 50 quantum wells. Then, when a bias voltage is applied to the Quantum Well Infrared Photodetector, the entire conduction band is tilted. In the absence of photons, the electrons in the quantum wells just stay at the ground states. When the photon is incident, electrons can be excited if the photons have the same or higher energy as the inter-subband transition one. The excited electrons will escape and then be measured as photocurrent. At this point, the thermal radiation is converted into a measurable electrical signal. Also, a part of the current, named the dark current, originates from at least 3 conditions without photons: ground state tunneling, thermal assistant tunneling, and thermonic emission. This part of the current is not cased by photons. That's all for a brief introduction of quantum well infrared photodetectors. Thank you for watching.